Alright, so I'm going to explain prelim, 2017 prelim, question 7, which is about virtual address spaces and the various amounts of size different components need. So for starters, number 1, or 7a, is how many bits are used for the page offset. So here's what we know. We're told we have a 40-bit virtual address space, a 32-bit physical address space, and we're told the size of a given page. So in terms of the offset, we actually only need to know we need one of these pieces of information for the offset. Because the offset is just saying for a given page, where do you go in that page? So all you actually need to know there is the number of different, the number of offset bits you need, is just based on the size of the page. So in this case, our size of the page, we're told, is 2 to the 14th. So our answer is just 2 to the 14th. Now, for the next part, we are told that there's a one-level page table, and we're asked how many page table entries must be stored in order to fit a one-level page table. So you keep in mind, our page table maps from our virtual address space to our physical address space. So the number of page table entries is going to correspond to the virtual address space, because it's basically you take a virtual address and you're going to go into the page table and you're going to come out with a physical address. So there needs to be a page table entry for each corresponding part of the virtual address. So our virtual address is 2 to the 40. So we have 40 bits in our virtual address. 0 to the 40. And we said before, we already know that the last 14 of those bits are an offset. And that's the size of a given page. So what's left, this part over here, is going to be the page number. Now this is the virtual page number. So if we want to figure out the size of the virtual page number, we have the whole thing is 40, and then it's just 40 minus 14 is going to be 26. So the question was how many page table entries must be stored. So it's going to be corresponding to the 26 bits, so it's 2 to the 26th. And that's B, 2 to the 26th. Okay, now for C, we have to suppose there's an inverted page table. So this is a similar question, except instead of a regular page table, we're talking about an inverted page table. So now, a normal page table maps from the virtual addresses, but if an inverted page table does the opposite. Inverted page table is based on the size of actual physical memory, and all of the addresses are based on physical memory. So in this case, we go based on our size of virtual memory, which is 32. We again have that last 14 being our offset. And then the rest of the address of our 32-bit physical memory is going to be our number of page table entries in our inverted page table. So then again we go this time 32 minus 14, which is 18, that's the 18 corresponds here. That's the 18 bits. So our number of entries is 2 to the 18. Now, for part D. Part D is the hard one. So for part D, we're told that we have a 2-level page table now, and we're told that the first level is accessed using the most significant 10 bits of the address, and then we're told that we have a process of 128 kilobytes, so that's 2 to the 17th is the size of our process, and we know how much memory is consumed by the first and second level page tables. Now there's a bunch of parts here. The first thing that we have to think about now, so we're told that we have a 2 to the 17 is the size of our given process. So the first thing that we're going to figure out is how many pages that takes up. And that's the size of our process. But we're not asked just about the size of the process, we're asked how much memory is taken up by our 2 page tables. So because it's a 2-level page table, we're going to have to figure out then it's going to be, so we know we have 1 first-level page table, and we're going to have to ask how many second-level page tables. And then after that, we're going to ask, so how big are these tables? And that's going to give us our answer. So we'll start with the first part. So how many pages does that take? This part's pretty basic. We have 2 to the 17th is our total amount of data. And then we have to show how much data fits in 1 page. So we've seen before that a page size is 2 to the 14th. So we have, 2 to the 14th data fits in a given page. The amount of data we have is 2 to the 17th. So how many pages do we need? 2 to the 17th divided by 2 to the 14th equals 2 to the 3rd equals 8. So that's the total number of pages we need. Now, great, that's our first part. Now our second part. So how many second level page tables do we need? So here we have to figure out how many pages does a page table fit in the second level. And the way we do this is we go about, again, breaking our addresses down. So look here, we still have the same 40-bit virtual address, right? So this is a 40-bit virtual address, and we still know that the last 14 bits are offset. So now we've got our remaining bits. Now the question tells us that the first 10 bits are for the first level page table. So this is the first. Now, what that means is that the rest of the virtual address is going to be indexing into the second level page table. And what that tells us here is that the second level is going to take 40 minus 14 minus 10, which is going to be 16 bits. So that's the amount of size that the second level page table is going to take. And what that also tells us is how many pages are going to fit, or how many page table entries are going to fit in one second level page table. So we're told here that it's 16 bits. So that means one second level page table is going to hold. So seemingly, so one second level page table is going to hold 2 to the 16th pages. So now we said our second question is how many second level page tables do we need? So if one second level page table holds 2 to the 16th, and we only have 8 pages or 2 to the 3rd that we have to fit in, so that's much, much, much bigger. So how many second level page tables are we going to need? Just one. Now, so we know we need one second level page table. Remember, we're trying to figure out now basically the total amount of memory that's being consumed as a result of this process. So we know we need one second level page table. You only ever have one first level page table. So we have sort of 1 first level, 1 first level, 1 second level, and then we just need to figure out how big these each are. Let's go some room here. Because we're trying to figure out how big are these tables, and that's going to be our total amount of memory that's being consumed. So for the first part, how big is the first level page table? So we saw before that it's marked out with 2 to the 10th is the number of pages in the first number of bits corresponding to the first level page table. So we have 2 to the 10th pages in that first level page table. However, we also saw that storing a page table entry takes 4 bits. So our first level is going to be 2 to the 10th times 4, because we have to store 2 to the 10th entries, and each entry takes 4 bits to store, or 4 bytes to store. So 2 to the 10th to the 2. Now that's the first level. The second level is the same kind of thing. Second level. And remember, so we're going to add these two. So then it's plus the second level. In the second level, we saw before, we have so it was this second level page table was 2 to the 16th, we said before. And now, because there are 2 to the 16th number of page table entries in a given second level page table. And again, storing a page table entry is going to take 2 to the second. So now we see here that the amount of memory taken up by these page tables is 2 to the 12th plus 2 to the 18th. But now the very last part of this is that the page tables are themselves stored in memory and themselves occupied in pages. And the one thing is you can't take half a page. We'd be allocating an entire page to the given process. So we're not actually quite done with 2 to the 12th plus 2 to the 18th. We need to ask how many pages these are each going to take up. So for our second level page table, it's 2 to the 18th. So we said before, a page is 2 to the 14th. So how many pages is that going to take? 2 to the 18th divided by 2 to the 14th. And that goes nice and evenly, and it's 2 to the 4th. So our second level page table takes 2 to the 4th pages. Just so. Our first level page table is 2 to the 12th in size. So how many pages is that going to take? If a given page takes 2 to the 14th, do we go to the 12th to the 14th? What that means is we do not, and that's going to be less than 1 page. So what that means is that for our first level page table, we need less than a full page. But the thing is, you can't allocate less than a full page, so that's going to end up being effectively, and for our purposes, equal to 1. So how many pages do we need? We need 2 to the 4th plus 1, which is 17 pages. And that's how much total memory we need. And 17 pages, as we've seen before, a given page is 2 to the 14th. So we need 17 times 2 to the 14th. And that's our final answer for how much memory is consumed by all of this. Now, let's wrap this up with part E. So part E, we have sort of a couple of different configurations, and we're asked about what's going to happen with all of them. So our first is a single level page table with no TLB and no cache. So we can do it this way. A number of levels. One TLB, no cache. So what's our minimum and what's our maximum it's going to take to get a given reference? So we have no TLB and no cache. So for a single level page table, what you have to do is you get your given call. You have to go into your page table, you go to the right thing in your page table. That's going to spit out the actual address in physical memory. And then you have to go to that actual address. That's sort of our pipeline. So the number of steps equals 2. And this is true for both the minimum and the maximum. There's no TLB and there's no cache. There's no way to get any better than this. So now our next step is our number of levels becomes 2. And we get no TLB, but we do get cache. TLB equals no, our cache equals yes. So what happens here, same kind of thing, except now we have 2 page tables to go through in our normal steps. Let's talk, the cache miss case first, which is the maximum it's going to take. So we're going to have to hit 1, then we're going to have to hit 2. We're going to get the address in physical memory. We go to the address, and the number of steps now equals 3. That's our worst case scenario. But now, our best case scenario is it's in the cache. And if it's in the cache, what we then have to do is we're still going to have to get the physical address. So we're still going to have to hit 1. We're still going to have to hit 2. But then we're going to get that address. Then we're going to go to the cache. It's going to be in the cache. Great. And that means our total number of steps there, which is the best situation, 2. Great. Now let's do the last part. So the last part, we have a 2-level page table with a cache and a TLB. All the things. Yes and yes. So our worst case scenario hasn't changed. Right? So our worst case scenario is everything's a miss. The TLB is a miss, the cache is a miss, nothing works. So you have to hit 1, we hit 2, first level, second level, go to the actual address. That's 3. The number of steps is 3. But now our best case scenario has gotten even better. Because now, first thing we do, we're going to hit the TLB. Check, we're going to get a TLB hit. We can skip out the first level page table, skip the second level page table, and then we go straight to the cache. Now in this case, we're saying, let's say the best case scenario is the cache is a hit. Great. And all we have to do is now go to the actual, go and get what's in the cache. And then, so in this case, our number of steps actually, a number of times we have to go to memory, just hit 0. Because we had the TLB, we had the cache, and we didn't actually have to go to memory at all. Wonderful.